that also binds oxygen. Right? And it has three different redox states. It has a fully reduced state, it has a radical, and it has a fully oxidized state. And so that should look familiar as compared to our study of flavoproteins and FAD, where FAD also can have 2 or 1 electron transfers. Right? And so that's crucial as a property of this guy, that it has the capacity to take either 1 electron or 2 and to donate either 1 or 2. And we'll see a model, if we get to it by the end of today, that for how complex 3 functions, that makes important use of the fact that this guy can hand off electrons 1 at a time. So these oxidation reduction reactions also involve the carrying of protons. The proton missing here, proton missing here. And so because it's H plus and E minus, which of course is typical, right, that also means that it's a suitable kind of cofactor. It does a kind of chemistry which is well matched not only to transferring electrons, but also to setting up a pH gradient. Because remember, what has to happen in this electron transport process is not only that electrons get transferred downhill, but somehow a pH gradient is set up across the intermitochondrial membrane. And so an enormous amount of research is ongoing still as to how that exactly works. And we do not have a good understanding of how it works yet. We have some models, and I'll show you a model. It's quite complicated that if we get to at the end of today. We won't have to know it in detail, but it's useful to look at it so you can see why Q giving 1 electron away in different places actually is important for how Q works. Okay. Any questions about this cofactor? You don't have to be able to draw it, just be able to recognize it and know it's got this chain and know about these properties. Okay, so the second one is the cytochrome. Cytochromes are proteins. Okay, there's a whole family of proteins called cytochromes. There's lots of different kinds of cytochromes. And what they have in common is that they're redox proteins, and typically they have heme-like groups on them of one kind or another. So here's heme B. Iron protoporphyrin 9 comes in different names. B-type cytochromes. A B-type cytochrome would have a B-type heme on it. Right, so these letters can be used with the designation of the protein or the designation of the cofactor, pretty much interchangeably for our purposes. Sometimes it's, there's A, and then there's A3, and then there's different C's, stuff like that, right? But if it's a C-type heme, then it's in a C-type cytochrome. So here's a picture of heme C, here's a picture of heme A. And you can see that there's basically the protoporphyrin skeleton, but around it are different decorations of functional groups. This has this long isoprene-based side chain on it, like a CoQ, but it's not a CoQ. It's just a defined structure here. And this guy is linked to cysteines. We won't have to know the details of why each particular heme is set up in a certain way. In many cases, we don't know exactly why. But it's good to appreciate that they all have hemes, and the decoration around the porphyrin skeleton is different. And that gives rise, of course, to different precise chemical properties, including, most importantly, the redox potential is different, depending on which particular cytochrome it is and which particular decoration of functional groups you have. Because you can imagine you can have more or fewer electron donating or withdrawing groups, and therefore that's going to change the affinity of the central iron for an electron or not, right? And so just very generally, we can appreciate that that's the case. And so that would be why, or a big reason why these heme-type cytochromes have reduction potentials that are kind of all up and down the table, right? So that's the same kind of phenomenon that we had with FAD, except in that case, FAD is always the same. It's always that same flavin ring. Right, so that's not different. In that case, what gives rise to the difference is differences in protein structure around the flavin. And here we can also have differences in protein structure around the cytochrome. So that can also contribute to the cytochrome differences in redox potential. Okay. So these are often integral membrane proteins, meaning that they're stuck in the membrane, or they can be membrane associated. There is an important cytochrome that is membrane associated, but also diffusible, as we'll see, and that is another essential aspect of the overall process. Okay. So we have coenzyme Q, we have cytochromes, and we have iron sulfur centers. Iron sulfur centers we've already talked about. A 4 iron 4 sulfur center like this would be, for example, what's in the enzyme aconitase and the TCA cycle. But here it is in its kind of more normal setting, where it's a redox cofactor involved in some aspect of this electron transfer process. Okay. Ferredoxins are small proteins that bind iron sulfur centers. They don't necessarily bind the 2Fe2S center, like this is a 2Fe2S center here. But you can have a ferredoxin. It can be also used as a general name of a protein family. You can have an FES center. You can have 2 FES centers of different kinds. Right? We kind of just say, oh, that's a ferredoxin. And we know it's a protein. It's got FES center, at least one, and it's transferring electrons. So when it's iron, whether it's iron sulfur or iron in hemes, it's on cytochromes, it's always iron 2 to iron 3. Right? It's 1 electron at a time for iron. Okay. 8 or more, it says 8 or more because we haven't found them all yet probably. But 8 or more iron sulfur proteins in the electron transport chain with, again, widely varying reduction potential. So now FAD, iron in hemes on cytochromes, iron in iron sulfur clusters, they all have reduction potentials that depend on the environments. Right? And none of those cofactors are diffusible either. Right? They're all like stuck on a protein. Right? FAD is not diffusible. And clearly, cofactors like this, once they're assembled and locked into a protein, they're not dissociating from the protein. Right? And of course, neither is the heme group. Okay. So this is just showing you a partial list of reduction potentials. So these are the ones that are the most important for the respiratory chain. So there's sort of for reference, the proton transfer to just form molecular hydrogen. But here we've got NADH forming NADPH, very similar. Right? Here's ubiquinone. Right? This is an FMN protein, and here are all these irons that have a range of different E'0 V values. And then at the very end, we have oxygen. So this very strongly positive standard reduction potential indicates that oxygen, molecular oxygen, has the most affinity for electrons of any of these species on here, right? So we know the standard reduction potentials for everything that is important, at least that we know about in the chain. This is an approximate order of transfer. I say approximate, and I may have annotated this slide to indicate the word approximate. This is not a fixed thing here. Right? We always have NADH and FADH2 to the left of Q, in other words, donating electrons to the oxidized form of Q to reduce it. And then we always have Q, right, over on donating electrons to a cytochrome, which donates electrons to molecular oxygen. Right? But where iron sulfur centers can sort of be in here, cytochromes can be in different places in here. Okay, so it's not like a one. This is a fixed thing. You'll see when we look at the details of some of the individual proteins that these chains of transport are so complicated that it kind of makes a mockery of trying to make an easy list like that. But nonetheless, NADH and FADH2 are deliverers, Q is in the middle, oxygen is at the end. That much is true. Questions?
I have
Yes,
a sort of quick question. So for the iron sulfur cluster, you say iron can only carry 1 electron at a time, and coenzyme Q has the ability to hold 2 electrons. So would you consider coenzyme Q sort of a regulatory point for electron transfer?
There is regulation of the chain, and we'll mention it. I'm not going to go into it in much detail. I would just, rather than saying Q is a regulatory point, I would say it's a crucial central cofactor whose properties determine how the chain works.
Okay.
And the key property, one of its key properties, there's 2 key properties. One is its diffusibility in the membrane, and the other is the ability to take 1 or 2 electrons.
Okay.